I'm Ali Yilmaz. I'm a professor at the Department of Electric and Computer Engineering. We are here today to talk about our bioelectromagnetics project that me and my students have been working on for about 2 years now, using TAC resources.
We are surrounded by electromagnetic fields that are generated by the wireless devices that fill our everyday lives. Bioelectromagnetics is the study of how these fields affect biological material like the human body.
The danger of cell phones, that's a very popular topic in press, and there are unknown things. We don't really know if they indeed cause, for example, cancer, right? The link between cell phone use and cancer is tenuous. It's not like the radiation from Chernobyl or Fukushima recently. It is a much lower frequency radiation. It's a non-ionizing radiation. What is as well established is the thermal damage. We know that cell phones radiate electromagnetic power, and just like your microwave ovens, if you turn up the power enough, you are going to heat and cook tissues. The open question is how much is too much, right? How much power is too much? So these computations, these simulations that we are doing are a step in the direction of identifying these limits and answering how much is safe, how much is not.
Since 1996, the FCC has required any wireless communication device sold in the U.S. to comply with certain safety standards. Device manufacturers have largely relied on standard anthropomorphic models, or SAMs, to measure the power absorbed by humans in order to comply with these standards. SAMs are essentially a head-shaped vessel filled with a liquid intended to represent your brain. They're subjected to electromagnetic fields, and a probe measures how much heat is absorbed. But SAMs don't accurately represent the complexities of the human body.
So we have found that if you are interested in the total power absorbed by the body, you can get away with very coarse models. But if you're interested in specific regions, right? If you're interested in how much power is deposited to the saliva glands right next to my ear, or how much power is deposited to this eye versus that eye, if you try to identify those, then the finer the model, the better the answer. So there is a significant improvement in precision.
For Yilmaz, this precision came in the form of a computational model. TAC researcher Victor Eickhout worked with them.
An anthropomorphic model will only take you so far. You cannot simulate sufficiently all the different length scales and material properties, inhomogeneities. So you have to go to a computational model where all that can be accurately captured. That will be both more accurate, realistic, and will give you a much larger set of data points.
With funding from the NSF, Yilmaz set about developing a richly detailed and precise model of the human body, the AustinMan. In the 1990s, a Texas death row inmate donated his body to science, which was used to create ultra-high-resolution scans. Yilmaz and his team took this publicly available dataset and, along with anatomists and researchers from the Institute for Computational Engineering and Sciences, transformed the images into complex maps detailing bones, tissues, and even blood vessels. This helps researchers track how heat travels through the body.
To be able to model blood flow is very important, and that you can only do with these finest resolution models. So we are able to now see blood vessels at details that we weren't able to see before, and this allows our simulations to be much more realistic and to include effects that were previously impossible.
As a result of these simulations, the researchers determined that low-resolution models can under- or overestimate the power absorbed by the skin, cornea, cerebrospinal fluid, and brain by as much as 50%. In addition to supercomputers, Yilmaz's students have also been integral to the creation of the AustinMan.
So I think this has been a very challenging project. There's been a lot of work that's been done on it. As you can see, developing the model from individual slices, we've already processed on the order of about 1,000 slices, and there are many more to go.
They are really the creative engine, the workforce behind it. I have been interacting with them to create the model, to develop the software algorithms, to come up with really ways to harness Ranger. I mean, they are almost like in a way race car drivers. Without a race car driver, you can't really get the most out of your race car. I would say my students are the race car drivers in this project. I am the coach sitting on the sidelines.
These simulations will not answer the question of whether or not cell phones are dangerous per se, Much about the dynamics of cancer and other adverse health effects are still a mystery to scientists, but they do represent one of the best ways of probing and quantifying the heating effects of wireless devices on the human body.
My wife jokes about the fact that after I started reading about this research in the field, we are no longer sleeping with our cell phones nearby. We simply put the chargers in a different room, so at night the cell phone is not nearby. We are doing some pragmatic things to reduce our exposure to these, but we are not really drastically changing our lifestyles. The evidence is not there yet, I would say, to take drastic action.